Now then, moving on to transformers. We've seen different kinds of text representation, such as one-hot encoding, bag of words representation. We've also seen word embeddings. All of these had some, disadvantages. Advantages, some of them were really simple, some of them are pretty expressive for words within text, but we didn't take into account certain aspects. For instance, how do they relate to each other? Word order has been an issue as well. And specifically for word embeddings, despite being very powerful the way they are, have this kind of disadvantage that they're not really put into context. We train them on data, of course, and by doing so, we do get a certain degree of implicit context within them for the cases that they were used in the data for different words. But that's kind of not enough. At least that's what some of the people thought when they invented transformers. So let's dive right into how we could improve our text representations even further. So, transformers were introduced in 2017 by researchers in a paper made by researchers from Google. The paper is called Attention is All You Need. And what was the main idea there? The idea is that we want to tokenize and convert text into vectors using word embeddings. That's relatively straightforward with the state of the research at the time, but then we want to also contextualize the tokens on each layer. Okay, contextualizing, great. Within a context window, using a so-called attention mechanism. And what does the attention mechanism do? Well, it amplifies key tokens while diminishing less important tokens from the entire thing. And so that's the big idea behind it. It's a mouthful, but let's have a look at how it might be done, or how transformers at least introduced it. But first of all, let's see what task the transformers were meant to perform initially. So, initially, in the Attention is All You Need paper, transformers were created for so-called sequence-to-sequence translation. As you see here on the left, you have a encoder and decoder parts where you give certain text to the encoder, pay attention, have the decoder, and then we can translate it from one language to another, for instance. At least that's the use case that was initially made for. And this is the architecture they proposed here on the right, with the left side here being the encoder and the right side being the decoder. Yes, so we'll go in a bit further detail into this today, seeing the different aspects of it. On one hand, we'll see that, okay, there's positional encodings. How do they come to be? What are they used for? And we have so-called attention heads, like the multi-head attention head here, one masked multi-head attention head, and these attention mechanisms, that's kind of the main contribution of this paper that we're going to look at into a bit more depth. So what would the inputs and the outputs here be like? For instance, you might have an input sequence of just land in Tokyo, and then an output sequence of gerade in Tokyo, and then you want to get gelandet out of it. So this is the kind of sequence to sequence translation task that was made for initially. But we'll set the focus now on the attention mechanisms. And why are there attention mechanisms here? The idea behind it was that we want to focus on what is important at the time. Different parts of a sentence might be important at different times. depending on what word we're looking at. Not every part of the sentence is always relevant for what we want to predict now, but sometimes we want to like focus on the beginning of the sentence or end of it or on specific words. And the idea here is that, well, we want to enable that in a kind of in our architecture. So what does it mean to focus on the important things contextually? Well, it means that we want to introduce context awareness. And the context awareness aspect here of the attention is what we're actually going to have a deeper look at rather. And what's also important is you have this other part here that I shortly alluded to before, the positional encoding. And the idea there is that we still want to keep track of word order, because word order matters in language. And yeah, so that's what we want to introduce here. So let's start a positional encoding and then move on to the attention mechanism afterwards. So positional encoding, why is it even necessary? Well, at this point, there had been some research, so-called recurrent neural networks had been used for these kinds of translation tasks to a certain degree, but there was an issue. Well, one of the issues at least was that you might have vanishing or exploding gradients due to the inductive biases that they get. For instance, when you're at the end of a sentence, you might not be able to have the path length for the information to make it through from the beginning of the sentence to the end of the sentence was pretty long, so it might just have gotten lost somewhere on the way. And the idea here is that, okay, let's try to encode position here still, specifically so that we can actually see at the end of the sentence, okay, this was at the beginning of the sentence. And yeah, we'll combine that afterwards with attention, as you see on the figure here on the right. But yes, we want to introduce word position information. And the idea is that the closer two words are, the closer we want it to also be mathematically. We want to be able to form a pattern that our network will be capable of identifying as well as possible, hopefully. So technically, for the positional encoding, we could just say 1 everywhere, 2, like for the first position, 1 everywhere, 2 for the second position, 3, 4, 5, and so on. But the people in the Attention is All You Need paper came up with something potentially a lot smarter. Namely, what they did was that they, as I already alluded to before, they wanted to have a pattern that would be recognizable by the model, and they would then compute it once and then reuse it for each sequence. That way, if we use it for each sequence over time, the model would then hopefully learn that, hey, this is a word, but it still has a certain relation to the other words that can be learned. The formulas that were chosen here were, well, the sine and the cosine formula. And you can see here how they're defined. For sinus of position divided by 10,000 to the power of 2i divided by d. Great. Okay. D is a constant here, well, as a parameter rather. But for how do we compute this based on our embeddings? How do you know what you have to use? When to use sine, when to use cosine? And the idea is here that, we have here, for instance, the embedding for just, and there we will go for every position of the embedding, and then compute either the sine or the cosine, depending on whether it's an even or an odd index. For the even indices, we use sine. For the odd ones, we use cosine. And in this fashion. So for the first one, since we say that, okay, 2i plus 1, with I being 0, you'd get 1. So E of just, you would use cosine, and then you use sine, cosine, and then you continue on until the end, where you then, well, at 512, you then would go to even 1 again. So the yes, so you have here within the positional embedding formula, you would have two arguments, the position, which is the position of the word itself, and 2i being then the position of within the position of the index within the embedding. And yeah, so in the end, you compute all of this here, and the researchers did choose these formulas for, well, good reason. Because when you look at this here, if we look at this graph on the side, if we increase the position, well, here it's just from 0 to 2000 something, and then the depth from 0 to 512, I assume, being the size of the embedding, you get these kinds of patterns, which is pretty interesting. And the hope is that would be easier for the model to recognize these patterns, or relatively easy for them to actually recognize it. So moving on. Attention is defined as follows. The attention of the matrices Q, K, and V is defined as the softmax as Q dot product K transpose divided by square root of dk, where dk is the size of the embeddings. And then after softmax, you still do the matrix multiplication with V. Cool. Well, the thing is, this was actually not an invention by the people from the Attention is All You Need paper, but it was already introduced in 2014, a few years prior, in a paper by Badanao et al., in a paper called Neural Machine Translation by Jointly Learning to Align and Translate, which is pretty cool. But now, let's have a look at this formula, which is very, very important even nowadays. So we have three matrices, Q, K, and V. Q standing for query, K for keys, and V for values. And here we have our softmax, our attention formula visualized. You have K and Q, you do matrix multiplication on them, scale them, optionally mask them, do a softmax on it, and then you do the matrix multiplication. The masking was mainly done, was actually done by the Attention is All You Need paper, but later on you have approaches such as BERT where they didn't do that anymore because they wanted every word to be aware of the entire context of all the words before and after, rather than Attention is All You Need. We mask away all the words that are after, so that they do not have any kind of influence on our current context. So we start with our matrix of embeddings. We have our just landed in Tokyo part of the sentence, each with a word embedding associated to it of 512 dimensions. And yes, so this will be the V, K, and Q matrix. So because we'll be doing this on itself, it's actually more correct, in quotation marks, I assume, to call it self-attention. The dimension of V, K, and Q is the same. Pretty obvious, since it's the same matrix that we'll be using. And this dimension will be the token count, which in this case is 4, and the embedding size, which is 512. So let's start by going into this formula here. There. Okay, the dimensions we already looked at, and this inner part of a formula will start with Q, with the dot product of K transposed, which is the numerator here on the softmax part, and intuitively we here have an entry in each part that will define the relationship between one word to another, between actually all the words that are within the other words. Because we started with token count embedding size, and then use transposed, which will then be embedding size token count dimension-wise, we end up with a token count x token count type of matrix. So we have this matrix here with word-to-word associations, just landed in and Tokyo. Cool, and here we have all the entries that are filled out. Intuitively, the diagonal should be the highest, right? Because the word itself should be the most meaningful for the word itself, which intuitively already makes sense. And here we also see where the masking can take place. We can set certain entries if we don't want them to appear later on in the weighting of the other entries. We can set them to -infinity here. Like we can set them to -infinity. For instance, we say that we do not want the later parts of a sentence to affect the prior parts of a sentence. How would you do that? Well, in practice, we'll just be setting everything above the diagonal to -infinity. So here, the landed aspect here would be -infinity to all of these 6 entries here. That way, we would only allow for the context to take into account what has already happened, what has already been seen, which can be what you want to have in sequence-to-sequence translation, for instance, as was done in this paper, actually, initially. And yes, so we have these kinds of values here. What do we do next? We want to then first divide it by square root of dk. dk being 256 here. It's a constant factor, so I'm not going to go into too much detail there, but then we do the softmax on this here matrix. And the idea of the softmax is it further amplifies the differences between the different entries. So we actually get to find out, okay, what's the most relevant word for this word right now? Okay, it's still itself. And well, if you know what a softmax is, as you should, then you'll see that the rows here all sum up to 1. Now, we have this token to token matrix with there's 4 entries here, 4 entries here, and we have a contextual relevance of 1 to 1. And we would like to now figure out the in-context relevance. The dimensions, token to token, as I said before. And what's now still missing out of this attention mechanism, or this attention formula here, is that we still do the dot product with V. So how can we do it? Well, we have our token to token matrix, and as we defined before, we have Q, K, and V has a dimension of token count to embedding size, meaning that now we can just multiply it very normally with V without having to do any kinds of resizing or other operations. So for this further self-attention, we'll take the multiplication of our word-to-word or token-to-token matrix do the dot product with the initial one. Yay. And why are we doing that? Well, the idea is that we want to capture the specific relation that we had before. We want to capture this in regards to all other words, and to this this serves as a sort of weight that we will just be introducing here into our initial matrix. So we have certain parts that will be pushed up and pushed down. The softmax made that, amplified that effect even further before. And now we kind of have a weight between 0 and 1 as a sum for each word, to then define, okay, how much we want this word to be pushed up and how much we want it to be pushed down, like to amplify or diminish its effect. And the really, really cool part about this here is we just started with a matrix and we continued working with the same matrix, which is honestly very cool because it didn't require any kinds of parameters. And yeah, honestly, this is kind of like in machine learning, you have hyperparameters that you're working with and that you might modify to get better results. And here, there's not really much to go by. The only thing that seems a bit more parametery would be the embedding size here. And usually that's kind of a given, it's a constant. But either you have, well, it's usually a multiple power of 2, like 512 or 1024 and such. But that's really interesting. Yes, as I told you before as well, why can we even do these direct multiplications with each other, or this dot product? Because with matrices, you always have to watch out for that, right? Yeah, this is just the dimensions again, that you have token count, and token count embedding size. And honestly, this is kind of very, very cool because we do all of these dot products, the softmax and such, and we end up in the end with the same kind of dimension of a matrix as we initially started, which feels very nice because we still have intuitively, we have our initial matrix. So everything we want to do with our initial matrix, we can still do with this new one now. So there shouldn't be too much loss of information, ideally none. And instead, we actually added more information, namely context, how the words stand to each other on their different levels here, in terms of like how important are they to each other. And yes, so that's honestly a really useful notion to have. Now that we have seen how the attention mechanism works from a math point of view and intuition point of view, let's get into what is called multi-head attention. The idea of multi-head attention is that, well, you might want to pay attention to different aspects or contexts of relations between all the words. And the way you do it is with a certain amount of heads, where the idea is that the specific head looks at a specific kind of context or a different kind of aspect, which is why let's have a look at the formula and how it's actually done. Yes, so there's a multi-head here. It utilizes the same 3 matrices we had before. It does a concatenation of the different heads with dot product of WO matrix. And there we also do the attention of the Q times WIQ, K times WIK, and V times WIV matrices. So the W matrices are weight matrices and they're parameterized ones, so that we can set different degree of different weights for each of the matrices, Q, K, and V respectively in there. So As we have seen the attention mechanism before, we'll now go a bit deeper in how you actually construct those different heads based on, well, the attention mechanism here. So for the multi-head attention, we apply self-attention to the entire input, right? But we only take specific parts of it as of the latent representations each time. So it might look something like this here, where we have the three matrices Q, K, and V each time with the dimensions token count, embedding size. And according to the formula that we have here, we also want to multiply them with the different weight matrices, ending up with these here. The different weight matrices, they have the embedding size times embedding size, a bit like what we saw before with how the words are related to each other in that regard. And it allows us to set different kinds of importances for different words in different contexts. So how do we continue from there? Well, we do the matrix multiplication. Well, we do the dot product of our input matrix with the weight matrix, and then we get Q prime, K prime, and V prime. So just from a dimension point of view, you have the token count, embedding size, dot product with embedding size, meaning the dimension we get for the matrix in the end is token count, embedding size. Yay, same as input, right? And now that we've done that, we then still have to see how we actually split all of that into heads. So in multi-head attention, the idea is that, as I alluded to before, is that one head implies one context. And the idea is that we divide the embedding, which in our example is of size 512, into as many pieces as there are heads. So, for instance, if we were to say that there's, how many heads do we say? For instance, if we say there's 8 heads for an embedding of size 512, that means each head would have 64 indices attributed to it, and so on. Like as in here, you see that, okay, you have the embedding of 1 up to embedding of 64, and then from embedding of 65 up at position 65, moving on, continuing further down until 128, and you split each time like that. And here the colors are meant to represent in what head they are. Okay, green is one head, blue is another, yellow or whatever color it is then another again. Meaning that all of our 512 positions are split into 8 heads with the same amount of embedding indices in them, as we present here. So we just take, for the first head, we have these embeddings, or these indices for the embeddings, the entries that we have here, that we take for each one. Then we actually compute the attention on it. And this will then be our first head. So as you see here, from the dimensions that you have for this head, the idea is that we have token count, like the amount of tokens that we have, just landed in Tokyo on one hand, but also then the embedding size divided by the amount of heads, which would be 512 divided by 8. How much is that? 2 to the power of 9 divided by 2 to the power of 3, so 2 to the power of 6, so meaning it's 64 for each of them, for both the head and the different matrices in it. So we do that for each head. We compute the attention for them, like for head 0, head 1, and head h minus 1. do it for all of them. Like in this case, it would be 8, as like we defined 8 before as the number of heads that we want to use. Hence, it's also useful to have, well, powers of 2 that we use there for both the embedding space and the heads. But it's not a requirement, just to be clear here. So what's still missing? We now did the attention for QWIQ, KWIK, VWIV. We did the attention for these matrices. Then we now have computed the different heads from head 0 till head h-1. Cool. Now there's only this part here still missing, the concatenation with the weight 0 matrix. And then meaning we just do concatenation of them, meaning that now that we have the different heads together of token count, embedding size divided by h matrices, dimensions wise, and we have that h times, means that we're back at a matrix of dimensions, token count, and then embedding size, which is really cool because that's what we started with in the beginning, meaning that all of our operations that we had before that we would do with our embedding, with our input embedding, we can still apply them now. It's just that the entries might look, or probably will look, relatively different. So, as a wrap up, for transformers, what we saw today was self-attention, multi-head attention. We also saw positional encodings or so-called positional embeddings. They're used pretty interchangeably. And yeah, they encode the position. The multi-head attention just splits the attention into different types of heads that we look at our input with. And the attention gives us more of a context and tells us how important certain parts are within, or how certain words relate to each other. So what transformers do is that what they did now historically is that they improved upon prior approaches for language understanding and latent representations, and they helped mitigate issues regarding vanishing and exploding gradients by effectively reducing path length compared to prior approaches for the information flow. And with that, we are done with the chapter on transformers. And next, we will have a chapter on BERT.